Hello and welcome to CAD Dimensions Lunch and Learn series. Today we're going to be covering Simulation Professional. My name is Franco Rotoli and I'm an applications engineer here in the Rochester office of CAD Dimensions. And let's go ahead and get started with our Simulation Professional overview. As some of you may know, simulation comes in three different flavors with SolidWorks. The highest level of SolidWorks you can purchase is SolidWorks Premium, which offers our static solver, our static analysis, as well as SolidWorks Motion. Leveling up from that, we have Simulation Professional, which covers these six additional topics: frequency, fatigue, optimization, drop test, thermal, pressure vessel. And then our highest level of simulation is Simulation Premium, which covers nonlinear studies, composites, advanced dynamics. For today's Lunch and Learn, we're going to be covering Simulation Professional. Today we're going to be covering Simulation Professional, mainly focusing on these four topics: drop test, thermal, frequency, and optimization. We're also going to look at some static studies as well. So let's go ahead and get started. For this first part of the demo, we're going to talk about a steering bracket where our goals are to keep the stresses below 150 megapascals, and we want to make sure that our frequency stays above 30 hertz. We also want to minimize weight. This is a steering bracket for a rally car, and obviously weight is important as well as strength. We want to make sure that this thing will not break in the middle of a race. So I'm going to jump over to SolidWorks, and we have the assembly modeled here. The steering bracket in question is this guy right here, so I'm just going to change my configuration to suppress all those other components. And the first thing we want to do is we want to create a static study, which again is in all the levels of simulation, including SolidWorks Premium. You can see I already have a static study here. If you want to see how this was set up, tune into our other webinars, and I go through how to set this up. But basically, we have a roller slider fixture there along with a fixed hinge, which keeps this basically bolted to the frame, and we have a force of 6,000 newtons on the ball moving in this direction. We can see the results here. Obviously it acts the way we would expect it to act. I can animate this. Okay, and we can see that the maximum stresses are in this area, which is what we would expect. Okay, so we're also going to run, the next thing we're going to run is a frequency analysis. But before I get into that, let's make sure that it meets our spec with the 6,000 Newton load. We can see our maximum stress here is 120 megapascals. So we know we pass this first test. Keep stresses below 150. We pass that because we're at 120 with a factor of safety of well over 2. All right, we're at about 2.25 in our highest area, so we're okay. So now let's make sure we pass our frequency test. To create a frequency study, I already have one created, but we can go to New Study and select Frequency. Now this is in Simulation Professional. Call it Frequency 2. And basically what we can do, and a beauty of SolidWorks and SolidWorks Simulation, is we can drag and drop components from one study to another. So this study, my static study, already has all my materials listed. I can drag my materials right into my frequency study. You can see that they get populated right in here. I can also drag and drop my fixtures as well as any loads. So let's go ahead and take a look at the parameters of this frequency study. We see we're looking at the first 5 fundamental frequencies, which is okay for our purposes, and I'll show you why in a second. I run this. Frequency studies run rather quickly. Okay, and we see our first 5 modes of resonance. Now, while these pictures are fine and dandy, they show me how the assembly is actually going to move. What I want to see is my resonant frequency. So we can see here that our resonant frequency, our first fundamental frequency, is at about 3,000 hertz. So we're nowhere near my 300 hertz, or my 30 hertz that I need to stick to. So back to the PowerPoint, we pass our frequency check. Now the next part is we want to minimize our weight. I'm going to do this with an optimization study. So I have my static study and my frequency studies done. I want to now optimize this for minimizing mass. To create a design study or an optimization study, again, optimization is included in Simulation Professional. And it works just like a design study does, except we check this box called optimization. And what we do here is we give simulation some variables to change. I already have a variable in here that's linked to the thickness of this material, and that's what I want to change for this particular optimization study. So I'm going to range from 3 millimeters all the way up to 6 millimeters in material thickness here. Now that's fine and dandy, all it's doing is changing dimensions, but I want to make sure that I still meet my other design criteria. So I have some sensors set up, and I'll set up a brand new sensor here to show you how it's done. But I have some sensors set up to monitor my other restraints. So to add a sensor, you can add one right here. And sensors are not only in simulation. Sensors are embedded within SolidWorks. You don't have to have simulation to use sensors. Obviously, we're going to use some simulation data, so you do have to have simulation. And I want to monitor the stress in megapascals. It goes in as stress 2. I want to make sure that that is less than 150 megapascals because that is my design requirement. My next one is my frequency. I want to make sure that my frequency is greater than 30 hertz. Again, my design requirement. Not really too worried about this because I was so far above that for my natural frequencies, but it's good to put in here because I want to make sure that I don't dip below or come near that 30 hertz. And the last thing I want to do, this is different than the design studies, I want to add a goal. My goal is to minimize my mass. And again, that's a sensor that I set up just monitoring my mass properties. When we have this all set up, we click Run. And I'm going to fast forward in time. This takes a few minutes to run. I'm going to fast forward in time and show you the results. Okay, so it looks like it has finished, and we see our results view down here at the bottom. And because it was an optimization study, we get an optimal configuration here, where my thickness is 4.5 millimeters. And we can see the stress results, 145, so we are under 150. And frequency, again, not really a big deal. And our mass is minimized. We can see there are other iterations. If I click on them, if you watch the model, you can see it actually change to those other configurations. This one, iteration 1, is actually in red or pink. That basically means that one of these factors did not pass. And we can see here the dark pink, the stress did not pass. This is above 150 megapascals, so it does not meet our criteria. So it lets us know very visually that this does not meet our criteria. If I click on optimal, I can go back to my model and my assembly has now been changed. So very quickly I ran, in this case this happens to have run 3 or 4 different iterations. I just set up a couple sensors and told it what to change. And you can see the different masses. Our optimal is 181.2 grams. Our maximum looked like it was 188. So about 7 grams savings, 7.5, 8, almost 8 grams of weight savings, which isn't huge, but you can picture doing this on your assemblies where the components may be a little bit bigger, a little bit heavier. You can save on shipping costs and things like that for mass. So let's go back to the PowerPoint. Now, with our brand new design, we have minimized the weight, we pass our frequency check,
and we also pass for strength. I could have also done something like a safety factor. If I wanted a safety factor of 2 or 3, I could have added that in. If I wanted to change more than one dimension, I certainly could have done that as well. For our next analysis, we're going to do a thermal analysis, and our goal is to determine the stresses caused by a thermal loading of combustion. So I'm going to add a heat source up here that simulates combustion. And we're going to see how that temperature propagates through our spark plug, and we're going to see the stresses caused by that heat distribution.
Let's take a look at how to set up a thermal study. Again, we just go to New Study, and we pick Thermal from the list. I already have a thermal study set up. I'll just walk you through how to do it. It works exactly the same way as all of our other studies. So we define materials. So I have plain carbon steel down here, silver at the node up here, plain carbon steel, and ceramic for the bottom. Okay, so obviously each one of these has different thermal properties. I added a temperature load, so rather than force loads, we have thermal loads. So you right click, I can add temperature, convection, heat power, heat flux, and radiation. I added a temperature load to these internal faces of 1,000 degrees Fahrenheit. I also added convection coefficients because these are going to be convecting or conducting to, in this case, the engine block. So this is going to be a convection coefficient of 0.0008 with an ambient temperature of the engine block being 300 degrees Fahrenheit. I also added a convection coefficient here, which is a little bit higher, 0.001, with an ambient temperature of 200 degrees Fahrenheit to the open air next to the engine block. We mesh it the same way, we run it the same way, and let's take a look at our results. So we have a temperature gradient plot where we can see here, obviously where I added the temperature, it's at 1,000 degrees Fahrenheit, and out here in space, in the open air, it's about 200 degrees, which is what we set the ambient temperature at. I can right click this and I can do some section clipping, which basically I can cut this in half so I can see the temperature gradient through my component. Just like every other simulation, I can right click and probe, so I can actually take points and I can see the temperature distribution through this component in this case, and I can also plot it on a graph. Okay, so I can see the temperature distribution through the thickness of my component here. You can also save that out to a comma separated file, so a CSV file that you can import into Excel. The next thing we're going to do is we're going to take this thermal study, because all this does is plot temperature gradients, and we can import this into a static analysis, a stress analysis, so we can see what stresses are induced by our thermal loads. To do that, again, we go to New Study, and we're going to do a static study. And this time, for our external loads, I can right-click and go to Thermal Effects, which brings me to this screen, and I can import temperatures from a thermal study. All right, I only have one thermal study in this case, which we were just looking at, but if I had multiple thermal studies, I could pick which one I import. And what that's going to do is it's going to add an external load that links it to this thermal study down here. Same idea, we can drag and drop materials, we can add any fixtures. In this case, what we're going to do is, because this is screwed into the engine block and there's a collar that goes around here, we are going to add an on-cylindrical face restraint on this face so that it cannot move axially or radially, or it cannot rotate either. because it's screwed into the engine block. Again, that takes a second to run, so I already have one created. And let's take a look at the stresses. All right, so we can see here that the max stress is about 2.5 million newtons per meter squared. We can also take a look at our displacements if we need to. So our expansion, we're looking at about 0.1 millimeters at this point, which is more than acceptable. We can also look at factors of safety, and it looks like our factor of safety, our minimum factor of safety is 0.1. We may actually be breaking this geometry. So I'd want to make sure that that 1,000 degrees was accurate and that this entire thing was actually 1,000 degrees. So you're just, again, going to want to be careful. This is going to give us some good insight into what's going to happen with our components. Okay. Moving on to our next study is going to be our next generation cell phone drop test. We can see we have a very advanced cellular phone here. So we're going to drop this phone from 6 feet onto this corner down here, and we're going to see what happens. We also want to determine if the screen will break due to the deflection. So the LCD screen that's in here, we're going to watch one of these corners and see what kind of deflections we get to see if our screen can withstand that. So let's go back in here to SolidWorks and open up this phone assembly. All right, what I did was I added a sensor. For those of you who don't know, you can add sensors in SolidWorks to monitor pretty much anything. You can monitor dimensions, mass. You can also monitor simulation results. So you right-click the sensors folder and click Add Sensors. So mass properties, dimensions, interference detection, etc. We're going to do simulation data and workflow sensitive, which monitors all simulation data. And basically what my sensor was is monitoring this corner. So let's go ahead and set up the drop test. So we click New Study and Drop Test. And setup for a drop test is very, very easy. All you do is you apply the materials, obviously. I'm just going to apply a material to all of these, and we'll just make this out of medium high impact acrylic. And we right click the setup where we define either the drop height or the velocity at impact, so I can fire this at the floor if I want to, or I can drop it from, in my case, from the lowest point. I want it to be 6 feet off the ground. I give it a direction for gravity. In this case, I have a plane that's askew a little bit, so that way it's going to hit on this corner. All right. If I wanted to change the target orientation, so if I wanted it to move, accelerate in this direction, but I wanted it to hit in a different direction, I could choose a different plane here. But in this case, we're just going to pick normal to gravity. I could also supply a friction coefficient to the target, or the ground in this case, and I can specify whether it's a rigid or flexible target. We want worst case scenario, so I'm going to keep this on rigid. I can also apply a critical damping ratio, so it'll actually dampen as it hits, or as the stress propagates through. We're going to leave that at 0 for right now. And we right-click Result Options, go to Define Edit, and what we're going to do is we monitor how long after impact. In this case, I'm going to do 200 microseconds after impact, and we want to save results starting from 0, number of plots 25. And this is where we monitor our sensor. Okay. We run this. Now this does take quite a long time to run because again it's doing it in it's taking loops and it's doing loops. So what I do is I already have this drop test run, and in the results we get the same results. So we see our stress distribution. And here we can see I created a very coarse mesh just for speed's sake. Our displacements, strains, and our response graph. This response graph is monitoring
that vertex that we specified in here. So it's showing the displacement of this point over time. So we can see here we actually probably didn't monitor long enough because it didn't settle out, but we're already at 1.4 millimeters roughly, or 1.35 millimeters. So in likelihood, the screen is going to crack because of the deflection at this point, depending on what the other corners do, obviously. And now for the fun stuff. This is what everyone wants to see, right? We want to see this thing actually dropping. So I go to my stress plot, I can right-click, animate that, and we can see it dropping, and we can see the stress propagating through. I'm going to change my resolution here real quick, just so it slows down a little bit more. Okay, so you can actually see the stresses propagating through the component. And this is up to 500 microseconds after impact. Again, I would probably want to do at least double this just to see exactly what's going to happen. Okay, we can see here that if I look to the right on my stress plot, we are past yield at some points, and we can see that the red is down here. So, and we can actually follow the max stress. It's always down here. So this is actually breaking. The acrylic is actually breaking. So from 6 feet, this thing does in fact break. Okay, so back to the PowerPoint. So we see the stresses when dropped from 6 feet, and we determine that the screen will break due to deflection in this area. It is very likely that the screen does crack.
Okay, in conclusion, today we've covered Simulation Professional along with Static Study, which is included in SolidWorks Premium. So we've done static, frequency, I showed you some optimization, drop test, and thermal studies. Stay tuned to our YouTube channel, and we will be covering other simulation topics along with other SolidWorks and other product topics on our YouTube channel and our Lunch and Learn sessions. I'm going to open up the forum now to some Q&A. If you guys want to use your chat function on the web meeting, then I'll be more than happy to answer your questions that way, or give us a call at any one of our offices, and any application engineer will be happy to answer your questions. Thanks again.